Hello, and thank you so much for coming to this session. I know you had a lot of things to choose from, and I hope I'm going to make this hour worth your time. My name is Tess. I work at Microsoft. I do machine learning. I kickstart machine learning projects. I have a few team members with me in the room too. And this hour is going to be about what the machine learning process is all about. So you're going to learn all the terms and basically what goes into machine learning. So we're going to start off with a very common machine learning problem, trying to classify, is this a chihuahua or is it a muffin? Okay. Who thinks that the far one is a muffin? Anyone? No? Everyone good for doing muffins for coffee? Or and who thinks it's a chihuahua? Okay. So you in the gray shirt, what made you think it was a chihuahua? Okay. Anything else that tipped you off? Maybe the ears, the nose. Yeah, a few things like that, right? So 20 years ago when we did AI and machine learning systems, we would have used traditional programming techniques to try to figure something like this out. So we would write code that looks a little bit like this. Basically, if the picture contains eyes and a nose and maybe some ears, it's a chihuahua. If it contains a paper cup, it's a muffin. And otherwise we just don't know. The question is, well, there are a couple of problems with this code. Picture contains is insanely hard to write without machine learning. Chihuahua is insanely hard to spell. And then you have to come up with all these rules. And people are kind of getting tired pretty quickly of coming up with rules. So what happens when you're met with something like this? Your eyes and nose, they don't really work. So what do you do if you have a problem like this, where you have to classify chihuahuas and muffins? Again, a very important problem. Well, one way you could go about it is you could use cognitive services, because cognitive services and computer vision it's already kind of a done deal where you can call a REST API, send in some pictures, and get pretty accurate information about what it is. You can also build your own neural networks by sending in a lot of chihuahuas and a lot of muffins, just labeling them chihuahuas and muffins, and let the computer figure out what the features are that make a chihuahua and a muffin. And it will create then this very long set of rules that it will, or weights actually, to distinguish between chihuahuas and muffins. If this is what you want to do, then this is already solved with cognitive services. A lot of things are solved like that, and I want to point this out because you shouldn't necessarily go in and do your own machine learning models if you don't need to, because a lot of times you can just use the ones that exist. Actually, let me just show you how that looks real quick to get that out of the way, because that's not what we're going to talk about today. So this is cognitive services. You search for cognitive services, and you'll find these REST APIs where you can try different images or try different text, depending on what type of cognitive service you're trying to look for. And these are very good ways to kind of infuse AI into your system. But that's if you want to go the pre-built way. And what we're going to talk about today is more how you build your own models for the cases where you actually don't have pre-built models. One thing I should mention about the cognitive services and the computer vision is it's a very generic kind of, for computer vision, it looks at it and says, it's a dog, it's cute, it's got all these features, but you might want to then differentiate between a chihuahua and a dachshund. Then you would go in and you would do something called custom vision, where you build on top of the already pre-built vision model, and you do something called transfer learning, where you use a pre-built model and then you kind of extend it and you specialize it to your own data. And even that is very, very simple. You send in maybe 20, 30 pictures of chihuahuas and dachshunds, and it will automatically build a REST API for you. So that is nice. But we're going to talk about those custom models, like, for example, face recognition and sentiment analysis, if you want to find out if someone is happy or sad in a picture, or in a Twitter stream, like text, if someone is happy or sad, you can use cognitive services. But, for example, for stock price, credit card fraud, movie recommendations, you have to build your own custom services. And we're going to go through a sample of something that I do a lot. So I don't know about Norway. I think it's the case here too, but in Sweden, finding houses is a national sport, right? Kind of here too? Okay, so I go to a lot of showings. In fact, I've been to so many showings that in fact my husband had to have an intervention with me where he wouldn't let me go to any more showings. And I found out that I did this for 10 years. I still live in the same house. And I was only kind of interested in the data. I was interested in how bids worked and how much houses would cost given parameters. So I figured, what if I take all that data and I use it for science instead? And this is what I'm doing. So these are some houses in Sweden, actually in my neighborhood. So you see the area of the house in square meters, and then you see the price in 1,000 crowns, which Swedish crowns and Norwegian crowns are, approximate. So you'll see that, for example, a 134 square meter house is like 5.5 million. The next thing I do, so I gather the data, and the next thing I do is I visualize the data and I try to explore it to find out sort of what the relationships are between different things. So I put them up in something called a scatter plot. This is something that you use normally to visualize like numeric versus numeric features, so area versus price. And I get this, all the dots pointed out, so somewhere around like 120, we have, or 100, we have two houses, like 4 million and 4.2 million, you can see there. So now the question is, if I want to use this and figure out how much a 150 square meter house is worth, what would it be worth? Anyone have a guess? 6 million? Who said that? Okay, yeah, you're behind the light. So 6 million is a pretty good guess. How did you make that guess?
Divided by square meters and multiplied back up.
Yeah. Okay, so divided by square meters and multiplied it back up. So somehow you got an average square meter price. Did you maybe do this in your head?
I guess so.
Yeah, okay. So, because if you squint a little bit, you'll see that this is a little bit like a line. And this line in machine learning terms is called linear regression. It's one of the algorithms used to do machine learning. So basically, you just try to fit a line, in this case, where you have two parameters, or a plane or a hyperplane, depending on how many parameters you'll have. And then you can use this. So once you fitted it to the data, like made a line kind of look fairly like the data, that's called fitting the model. And once you have that, you now have a model which is the actual line. And that model can now be used to figure out how much a 150 square meter house is going to cost. And if you look a little bit, you'll see that 150 square meter will land us around 6.2-ish, right? So that is going to be our guess for how much a 150 square meter house is going to cost. Now, everything in machine learning is a guess. You're never going to get exact science. It's a little bit like you have input parameters, you have a black box function, and then you have an output. But that output is not like we're used to going to be an exact number. It's just going to be a prediction for what we think. Because if you see, for example, for 100, we'll see that one dot lands on the line, but the other dot doesn't. And both are obviously houses that were sold. So one of them was slightly off. So the question in machine learning is more, how off are we? Like, how bad is our guess? And to find that out, what we do is we use a marker, and we do something called a confidence interval. So we just basically draw a marker around where the dots are and figure out that that's basically how bad or good we're going to get. And if you look at how far off we are, you can say, okay, so we're going to guess 6.2, give or take 500,000 crowns. Obviously, more will be closer to the line. And what we want to do is we kind of want to narrow down this confidence interval to make it a tighter and tighter fit. This is the whole process of machine learning. So once we've gone through the sample, we've now gone through everything. We've asked a sharp question. What is the house price going to be given some input parameters? Collected data, explored the data, also cleaned it up. If we go back one step, we'll see that I initially put down 40 million for a 98 square meter house, which obviously is a little bit expensive at least for Sweden, maybe not Norway. But if we would have put that dot on there, that error dot, what would have happened to the line would be, go like this, right? Instead of like this, it would kind of be skewed like that, which means that our whole model would be off. So we want to try to eliminate those outliers, or those error values, or those values that don't necessarily fit into the general trend. Then we want to transform features. I'm going to talk about that in a bit. We select an algorithm. In this case, we selected something called linear regression. Regression is, I'll get to that later. We train the model, so fit the model to the data, use the answer, and then eventually we'll also retrain the model, because as things change, like as laws change for how much you have to amortize and that kind of stuff, the model will have to be adjusted slightly. So we'll go through these one by one. The first one is asking the sharp question. And this is something that most people miss when they think about machine learning but have never done it. People usually come in and want to do machine learning, and they want to create some kind of brain that will learn from your data, but they don't actually have a set goal for what they want that brain to do. And that is what asking a sharp question is about. If you don't have a goal, you're never going to get a good machine learning model. So it turns out that there are only 5 different questions that you can ask machine learning. First one is how much or how many. How much is the house going to cost given these input parameters? What's the stock price going to be? What's the temperature going to be? How many people will buy? Blah, blah, blah. So a numeric value, and that's called regression. So that's kind of where our linear regression algorithm came from. The next one is called classification. And that's a question of, is it this or that? Is this email that just came in, is that spam or not spam? A person with all these symptoms, does she have diabetes or does she not have diabetes? Or a news article, which one of these maybe 5 topics is it about? So it doesn't necessarily have to be binary classification, like one of 2 classes, but it could be more than that also. And then there is one specific case of classification called anomaly detection. So anomaly detection is when one of your classes is super, super small. And that's usually the class that you actually want to identify. So for example, with credit cards, you have a lot of transactions, and most of them are good, and then you'll have a few fraudulent ones. Like let's say in 1,000 transactions, you might have 1 fraudulent one. Then what would happen if you would use normal classification? You could go in and say, not fraud, not fraud, not fraud, for 100% of them, and you would be 99.999% correct, right? Is that a good model? Maybe not so much. So in that case, you have to use either other algorithms or you have to fix your data in some way. So one way to fix your data in a case like that is through upsample the fraud transactions. So you generate like a lot more fictitious fraud samples, but based on the fraud samples that exist. Or you can downsample the good ones to make the classes a lot more even. So all of these 3 are part of something called supervised learning. And supervised learning is when you have input parameters and the output, and you have a lot of samples of input versus output, and you're trying to find a function that maps the input to the output. That is what supervised learning is. Then you have another kind of machine learning algorithms that's called unsupervised learning. And in unsupervised learning, you don't have input versus output. You just have a bunch of input, and you want to make some sense of it. So one of the ways to make sense of it is, for example, to cluster your data, to figure out which ones are similar in some way. You don't necessarily tell it how it's similar, but you want to find out which ones are similar. So typical usages for this is if you have a Netflix, if you're at Netflix and you want to recommend movies to someone, then you might want to cluster either the people to see these people are kind of similar. Maybe it turns out that it's going to be like 30-year-olds that like Metallica and have never been to Burning Man. Like that might be a group. You don't know what the group is going to be. But maybe they then, because of the similarities they have, turn out to like the same kind of movies. Or maybe you'll do a clustering of movies and say, these movies are sort of similar, but the difference between this and classification is, in classification you would say, which ones are sitcoms, which ones are dramas, which ones are blah, blah, blah. And in this case, you just want to have like an undefined similar group that may like, and that if someone likes one of the movies, they might also like the other type of movies. Does that make sense? It's a little bit, that's probably the big, hardest difference to understand. But the fifth one is called reinforcement learning. So reinforcement learning is when you're in a situation and you're trying to figure out what you're going to do next. So this might be like an autonomous car, or in this case, like a vacuum cleaner, a robot vacuum cleaner that needs to figure out if it's going to go back and charge, or if it's going to go and get some more dust. And the way that works is that you usually have a simulation where you simulate all the different actions that you could take, and then you get positive or negative feedback. Like think of it as, for example, if my cat was doing machine learning on me, and I gave her all these treats, and then she sniffed one and didn't like it, and then she sniffed one and really, really liked it and munched it down. And then I'm always going to buy that one. So basically, it's optimizing the road you're going to take moving forward. So these are the 5 questions that you can ask machine learning. And then you go through and collect data. Yeah, that went well. And you can collect data, of course, in a million different ways. This is going to probably be one of the biggest tasks in your machine learning projects. But I want to point out 2 sites, Kaggle and Uci. So Kaggle is a machine learning competition site where you can actually go in and make some good money doing machine learning. Like here, for example, if you're really good at credit default risk assessment, then you can win 70,000 grand. But there's also a lot of like training data sets that you can use and practice on. So you can grab things from there, and you can go in and figure out what other people did. So other people will put all their code for when they went through and analyzed this problem and did machine learning on it, and you can just kind of follow their ideas. Also, there's a good learning place here where you can go through exercises and learn machine learning. But when you've gathered your data, it's going to look something like this. Kind of like an Excel spreadsheet. And this is specifically for supervised learning. So you'll have a bunch of, like first you have a target. This is what you're trying to predict, the house price. And then you have some input parameters that are your features or your inputs. And because machine learning is always going to come down to a math equation. So that means that your features are always going to have to be numeric, because math is like not super good at strings. So what you do then is, for example, the first one, the area, that's a number, so we're good. And the second one is a category, of course, if it's a house or a townhome. And in that case, you might turn that into 0 or 1 based on if it's a house or a townhome. And then you'll end up with some numbers, like the zip code, where you don't necessarily, like it is a number, but it's not a number that you want to do math on. You don't want to multiply zip codes. You don't want to subtract zip codes. And maybe just because it has a higher zip code doesn't mean it's better, that type of thing. So in that case, you also have to turn it into a category. And you do something called get dummies, where you basically create a lot of columns of, is it 90210, 0 or 1? Is it 11436, 0 or 1? That kind of thing. All of these elements are called an instance or a sample or an observation. So that is just one input versus output. Once you have these, you now try to figure out which features should I actually use for my machine learning model. And there are basically 3 rules of thumb that you want to look at. The first one is it relevant for the task at hand? So similarly to when you create a function, you just want to have parameters to your function that actually matter for the output. It doesn't make sense to just put like random things in there. So when you think about relevant, you might think of like distance to the water, super relevant, at least in Sweden. The number of chickens that they sold in Alabama at the same time they sold your house, iffy at best, I would say. And then you have some that you don't necessarily know if they're relevant or not, like the broker. Maybe the broker does increase your house, but maybe it's an afterthought. Maybe some brokers just pick more expensive houses. So in some cases, you want to kind of try to figure out what's the cause and the effect. And then you pick the ones that seem more relevant. They also need to be independent. So if you have the area of the house in square meters, you don't actually also want to have the area of the house in square centimeters. And the reason for this is because if you do, a lot of the algorithms that we use in machine learning will then take double notice on the area, which may make other features less important to the model. And you might think, okay, so I'm not stupid. Why would I put like 100 square meters, 120 square meters, and also 120, well, 1.2 million square centimeters? And you might not, but would you, for example, maybe add the number of rooms? So the number of rooms in this case could actually tell you a lot about the area, because at least in Sweden, an average room is like 25 square meters. So given the number of rooms, I can almost always tell what the square meter area is. So you want to kind of remove those ones that are super highly correlated. Correlated meaning if you know one, you almost always know the other. So like if it has over like 70% correlation or something, you might want to pick one or the other. And the one you pick is usually the one that's more correlated to the end value that you want to look at. So relevant, independent, and simple. So simple means that sometimes you have something like a GPS coordinate. Yeah, awesome for us. When we look at houses, we can tell exactly where the house is, and it gives us a lot of information. For math, GPS coordinates is a really tricky thing to deal with. Like again, kind of like the zip code, you don't know if a higher coordinate is better or not. So instead you want to transform this into something a lot more useful. Like for example, how far away is it from a lake, or from the city center, or from schools, or what region is it in, that kind of stuff. So you take some complex coordinates, or sorry, complex features, and turn them into maybe a lot other more useful features that can be used by math. And then you go through and explore the data, and you look for a few things. You look for example, for duplicate observations. So when I brought down all the sales data for our houses, then I found out that first I had the house price when they were sold, and then I had the house price when they were transferred to the new owner, which was a little bit different because it was sometimes adjusted, but it was essentially the same house over and over again. And I had this for maybe 50% of the houses that I was looking at. In that case, you want to remove the observations that are for the same house so that that doesn't get counted twice and sort of skew your data. So duplicate observations. You also want to look for irrelevant observations. So in this case, it means that if I want to create a model for how much a house is worth, I might not want to include like apartment prices, because apartment prices have totally different patterns to them. Apartments are usually more interesting if they are in the city center, whereas houses might be more interesting if they are outside with green areas and that kind of stuff. So try to separate out into models that make sense. So don't try to make like one big model. Instead, try to group things that do make sense. Next thing is outliers. So we've already seen like the 40 million house, because we know that's going to skew the line like that. And sometimes you might have ones that are not actually errors, but maybe you have like a super big house, or maybe you have a house with a lot of land area, and it just happens to not fit the norm. In that case, you might want to think to yourself, okay, so should this model actually handle these houses? Maybe I'll cap my model for houses that are less than 300 square meters or something. And you want to deal with missing data. So missing data is when you have a math function, it doesn't really make sense to have some of the numbers missing. So then you have to fill them in, and you have to think about like sort of where the missing data is coming from. So when I gathered all my house prices, I noticed that, for example, some of them didn't have a monthly fee, which is normal for most houses that are not condos, like that you don't, well, you don't actually own the house, but you own just the right to live in the house, and you have sort of a rent. And in that case, I would replace that with a 0. But in other cases, you might see that it's missing, but you want to replace it with like an average, because that makes more sense. It was just missing, but it should actually have a proper value. And then you look for structural errors, like free text fields where people have put things in, and you want to make sure you gather them into neat categories. And when you look at categories, you want to at least have like maybe 30 samples or something in each to make them statistically relevant. Because let's say you had, for example, only one person in a certain zip code, then that house, like whenever that zip code comes in, your algorithm might give it the same price as that one house in that zip code, because it couldn't do any statistical analysis on it. And then you clean the data, and then you go through and transform the features in the way I was talking about, like moving the GPS coordinate to how far away it is from something. But another very typical one that you'll deal with is something like this. If you're predicting ice cream sales and you have the date, while interesting, doesn't give you a whole lot of information. But if you instead transform it into, is it winter or summer? Is it a Sunday, or like is it a weekend, or is it a normal day? Are the kids off school this day? Stuff like that will definitely give you a lot more information about what your problem is, and give you a lot better, like be a lot more relevant to your problem. So these are a few things, a few tools that you can use to analyze and do this cleaning in. The first one on the far right is, on the far right. Sorry, I can't tell left from right. Need to do some machine learning. It's Jupyter Notebooks. So that's a way to run Python in a browser, and we'll look at that in a second. And the middle one is Azure ML Studio, which we'll look at later. But I just wanted to point out that you can use pretty much whatever tools you want. Like if you want to use Excel for the cleaning, or SQL, or whatever, that's quite all right too. So let's take a look at the Jupyter Notebooks. So there is essentially two main languages for doing machine learning. It's Python or R. There are some new ones, like we have ML.NET and C#, which you can start off with, but generally people do it in Python and R. And usually if you're a developer, you'll do it in Python, or if you're a math person and come from that environment, you'll usually use R. And they're both very good because they have a lot of visualization power, they have a lot of machine learning libraries, and they have all like the big deep learning libraries are built for Python and R. So this is a Jupyter notebook. And the cool thing about Jupyter notebooks is you'll start off like you used to run a Jupyter notebook server. And now you have something where you can actually write code and run them cell by cell like this. And whatever you run in the first cell, that context is still going to stick in the next cell. So even if you don't want to do machine learning, it's pretty cool and nice to work with Python in this way. The other cool thing about Jupyter Notebooks is that you can mix it up with markup, which means that you can create a story about your data or about whatever you're trying to develop, and then pass it off to the next person that can actually run this notebook later. So in this case, I bring in like a CSV file. Here is the data. And then I go through and I do some analysis of the data. So this is a diagram that I used where this column right here is the monthly fee. This column here is the land area. And the yellow ones are the ones that are missing. So if you look, you'll see that they're kind of mutually exclusive. So whenever you have a monthly fee, you don't have land area and the other way around. And that is because when you have a condo, you don't actually own the land, so you don't have land. Land exists, but you just don't show it in the ads. So what I do with something like this is I fill the monthly fee with 0 for the ones that don't have it, and then for the land area, I estimate how much land area you would typically have for this size house. So I would do like an average based on the size of the house. And then I might also create a new, I do like a feature transform, and I create a new feature called isCondo that I might use as an input parameters. So that's sort of the way you move through that type of data. Then for structural problems, like so here is a bunch of regions that were listed, and these are free text regions. So this means central Sollentuna. Sollentuna is my neighborhood. Then it's like Sollentuna Centrum, and yes Sollentuna, and then some capital letters Sollentuna. And then you just go through with regular code and kind of transform this into categories that have more than just a few samples and kind of bring them together. And this is just one way to do this, or like if you were to do this in like Power BI or some other tool, you could use some other functions for doing this. Then I would go through and I would visualize the data a little bit to see things like, here's the price. I have a lot of like, here are most of my houses, and then I have some oddballs up here. So I might want to look at why are these so expensive, and do I want to keep them in my data set? I look at trends, and I find out like for townhomes and detached houses, the trends look approximately the same with an offset, so I can use them in the same model. I look at some of the oddballs that were like very expensive, find out that they're by a lake. So then I say, okay, so maybe I want to add a feature if they're right on the lake or not. And that is essentially how you go through and look at the data. So all of that I've been talking about for the last half hour is going to be 80 to 90% of your machine learning projects. Sorry to say. Because the next part is what people usually think about when they think about machine learning, like the algorithms and the math and all that stuff. I'm not going to get super mathy, I used to say that, but just remember that when you get into a machine learning project, what we've just gone through, that's going to be the majority of of what you're going to look at. And that is where you have to also be super critical about what you have. Because it turns out that just like with a function, if you have crap in, guess what's going to come out at the other end? It's not necessarily going to be pretty stuff. But we have all the data in a nice format, so now we're going to select an algorithm. The first one we've already looked at is linear regression. We fitted a line. But how does it work? How do you get from that visual representation to something that you can actually use? Typically, if you would do this as a developer, you would probably do something like this. Create a function, like ask one of the realtors and say, hey, can you come up with some numbers for how much do you pay for like a starter house? So any house, let's start with $10,000 and then 6.7 per square meter, and then add an extra 20K if it has a pool, and then 10K if it has a kitchen, 5,000 based on some neighborhood quality index that I build up of the region, whatever, and you come up with sort of a math function like this, right? This is pretty typical function for these kind of things. Problem here is that how do you come up with these numbers? And what if this guy who gave you these numbers was working in New York and you're working in Sweden, so these numbers really don't fit? Do you have to come up with like a new one of these functions for every single area you're in? And the answer is, instead of having like some random person give you these numbers and just estimate, you can do this by taking all that data and making the data work for you and give you all these weights. So the way it works is like this. Let's go back to just one parameter in. So we're looking for the weight, or basically the square meter price in this case. The way this works is we'll start off with a line, just a random line. And then here, what you have is something called the loss function. The loss function calculates how far away the dots are from the actual line. Basically, how wrong are we in this case? What's our confidence interval? And it's like, in this case, it's very simple. You just take the distance and you square it, and you take the absolute values and a few other things, but you come up with this line. And you can see I picked a really low square meter price, so I'm very wrong, right? Then on this curve, on this cost function, or this loss function curve, I now take, I'm just going to mention like some math term, like we're going to do gradient descent, which is basically you look at the derivatives, which is basically you look at the slope of the curve and say, which way slopes down? Oh, this way. So I'm going to take the next one, like we also use a parameter for saying how far away on the curve should you go. So I'll take the next one, and we get a slightly better line and a slightly less cost. And then you go through and do this until you get to the bottom of this curve, where no matter where you look, left or right, it's always going to be up. So there's no point for you to move anywhere else, right? And this is like now our minimum, and this is going to be our best fit for the line. And what you see down here, like the difference between the dot and the zero line, that's how far off you are. Like that's how bad this guess is. But we know we can't get any better than this. This algorithm was invented sometime in the 70s, I think. This is the linear regression algorithm. We use it still today, but it only works on very linear problems. It only works if we can sort of do a line or a plane or something like that. And usually you don't necessarily have very, very linear problems, but we'll get to how you can fix that in a moment. But just know this, because this is one of the base functions that we use. The next problem we can run into is classification. So in this case, we have apples and oranges, and we want to split, we want to figure out if it's an apple or an orange. How would you do this? Does anyone have a guess on what we could use to separate the apples and oranges? Color? Yeah, color would be a good one. But if we only have sweetness and acidity, like, could we do it visually in some way? A line? Yay! A line. So yeah, we would use a line again to do this, because this is also a very linearly separable problem. Like we can use a line or a plane or something to separate these. And you'll see that some of the dots, like this one, this apple lands on the orange side, this one lands on the orange side, which is fine, because again, it's a prediction. It's not going to be an exact function, right? But we can also probably say that the further away from this line we get, the better off our guess is going to be. Like, so here we're going to be a little bit unsure, but further away we're going to be, the better our guess is going to be. So what we do here is we use the same linear regression method with the cost function and everything to figure out how we're going to place our line. And then we kind of write an S, like we use a logarithm curve. It's called a sigmoid, that says if you're far, like at one point, like basically somewhere around here, the S goes like this, and everything above here, we're very sure that this is an orange. And if we go down here, everything here is an apple. So picture an S like this. But here, like, we're a little bit less sure. This is called logistic regression. So it's called a regression because it's using a line here, but it's just another function at the end, like an S applied to the function. Now, this was also invented in around the 70s, but what has happened lately that is make, sorry, I'm going to bring it back so you can take a picture if you want to. Yeah. So what has happened lately that's made this a little bit more interesting is this. We've gotten a lot more data, a lot more data. We have data everywhere. We also have a lot more computing power. Like we have clouds and we have GPUs and we have different techniques for doing these things with vectorizing and parallelizing it super well. So both computing power and better algorithms have made us able to do something like this. A neural network where we train a lot of these logistic regressions or a lot of these linear regressions and basically just couple them together. So neural network is just that. It's basically just a group of a lot of linear or logistic regressions depending on which activation function we use. So activation function might be the S, or it might be something that looks more like the linear regression. So what does this give us? Well, we've only worked with linearly separable problems before, which not all data is linear. Let's say, for example, you want to figure out if a person is going to go to a Metallica concert. Well, you might have some that are up to 15 or maybe 39 that won't go. And then you have some, like me, that will go up till a certain age, then they won't go again. So it's not like the older you are, the more likely you are to go to the Metallica concert. So that's a typical nonlinear problem. And the way we do this then is by combining these, we can now fix, or we can now look at nonlinear problems. So one of these steps might say, okay, so I figure out the feature, it's a family-friendly house. I figure out the feature, and this is a house that's made for young professionals. This is a house that's in a school district, like in a really good school district. And then it combines these new features it created, and it then combines them in the next layer to maybe something a little bigger, and eventually to the proper price. If we would look at this like as an image coming in, the first step would kind of look at like straight lines, and the next step would make them into squares or circles or maybe color blobs, and the next one would turn them into eyes and ears, and the next one would turn it into a chihuahua. So that's sort of the stage here, except for image neural nets are usually way wider, but neural nets for these simpler problems maybe have two layers and maybe, I don't know, 5 hidden units on each. Like that's all configurable. But that's why it's gotten so interesting right now. So that's neural networks, just in a few steps. There are a few other algorithms that also work on nonlinear data. So two of them. The first one is called decision trees. So here we're trying to figure out if someone is going to play tennis or not, to kind of staff up our tennis shop. So what we do is we play a game of 20 questions. So if I'm thinking of a person, and you had 20 questions to ask me, what would you ask?
Gender?
Yeah, like gender, male or female. And why?
Because then you already have 50%.
Yeah, exactly. So once you've asked the question of, is it a man or a woman, and they say it's a woman, then you don't have to worry about like all of these people. And the same way is kind of how decision trees work. You try to split the data up and try to kind of like remove as big chunks as possible. So if we look at this data set and we just look at the ones that have yes, is there something we can say that can tell us immediately like if it would be a yes or a no? And the answer is, like if it's cloudy, they will always play. And then we'll go through and look at if it's sunny, then we'll see that if it's humid, they won't play. If it's not, they will play, and so on. So we'll go through, And we end up with these if-else statements, like sort of like a decision tree. And this is now basically how we either classify or give the numbers for our houses. The problem with this is that oftentimes this will learn the data by heart. So it will learn every little intricate detail about the data if you let it go far enough. Like if you let this have like, I don't know, 100 different if statements, eventually it will say, hey, if this guy is called Pete and he has $5 and he makes a transaction on a Friday afternoon in May of 2018, then it's a fraud. But that won't necessarily generalize super well to future data. So what you do then to avoid that is that you have some training data that you train on, and then some test data that you verify your model on, so you know that it actually, what it's learned is actually generalized. But you also do something called ensembling, which is where you take a decision tree and you say, you can only be this high, and you can maybe only look at like the outlook and the temperature, and some other tree looks at the humidity and if it's windy or not, and make decisions off of that. And then you go together and you vote. So you create, instead of a decision tree, you create a decision jungle or a decision forest. It depends a little bit on how this voting is made and what it separates on. So that is how you avoid that problem. And then one last algorithm is it, in this case, we're trying to figure out if an email is ham or not, if it's spam or not spam. And we're going to use an algorithm called naive Bayes. So in this case, we have some spam email, some not spam email, and we have some that have a spelling mistake. So we'll remove the rest, and we'll say, okay, so given that it has a spelling mistake, what is the likelihood that it is a spam email? And I'm not going to have you do math this early, so it's 75%. And then we go through and do this for a bunch of other things. Does it contain the word sheep or free? Does it have no title? Is it from a certain country? Is it sent to 30 people or more? All of those things that you think that maybe make an email a spam. And then you combine all these probabilities in, it's just a simple math function to combine the probabilities, and you get an ultimate probability of, is this a spam or not? And it is also a way to work with very nonlinear features, but where the features are kind of totally independent from each other. So you have all these algorithms. Which one do you choose? So it turns out that some of these algorithms are made for regression, like made for finding the numbers, some are made for clustering, some are made for classification. But apart from that, there are a couple of tricks that you can use to figure out which one you want to use. So this is a cheat sheet from Azure machine learning. There is a lot from like scikit-learn, which is a very popular Python library. And there are lots of cheat sheets like this. I'm just putting this out not so you have to read it, but just so you know that there are these cheat sheets. But what you would do is, you would do first one thing, you would spot test a bunch of algorithms and see which ones seem to fit your data best. Like maybe a linear algorithm or maybe a nonlinear algorithm like that. And you will always find that it's going to be like a neural network if you have enough data, or a decision tree based algorithm. Like that is basically, yeah, hint. It's always going to be your answer. But anyways, you would spot test anyways to see sort of which one to use. And then you go through and you train the model. So you train it, you input the data, you split the data up into training and testing. So 80% for training, for example, and 20% for testing. You choose your model, linear regression, train the model. You then use the trained model to predict the answers on the test data. So you just guess for all these inputs, what is the output going to be? And then you figure out what your confidence interval is going to be. So let's see how this works in real life. And I have to say, typically you would do this in Python or in R, but there are also really good tools for doing this visually. And especially when you're starting out with machine learning, this might be a very good way to kind of get started. And there are actually some very big companies that use this as their model, so it's not like you can't use it for real. So what this is studio.azureml.net, where you can just log in with any kind of Hotmail, Live, Outlook account like that, and you can train for free for quite a while before you have to pay for anything. So what you do is you either take data sets that you have in some storage. It can be in Azure, or it can be somewhere else. There are plenty of ways to import data. In this case, I picked a CSV file, and I just uploaded it. And you just go through and you drag and drop things like this. So here I've dragged a data set, and if I look at what this data set looks like, it's going to have like my house type, my region, area, and so on. So if I look at, for example, the area and compare that to the price, we'll get a scatter plot very similar to what we saw in the earlier ones, except for it's a lot thicker because I put a lot more data in here, and it turns out it's not that nicely lined up, but there are ways to fix that by making like log scales, for example, to make it more straight. And you might look at something like the region and compare that to the price, and then you'll see that some regions are more expensive than others, and some have some outliers and things like that, and you might want to clean it up. So this is just kind of to verify that you have all your ducks in a row. The next step is going in and editing the metadata. So recall that I said in the very beginning that everything has to be numerical. So what you do in here is you say these fields, like the house type, the region, blah, 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 they're categorical. So I want to turn them into ones and zeros, or a bunch of columns with ones and zeros. Then I select a few of the columns in the data set because I might not want to have all of them. Maybe they're not all relevant, independent, easy like that. So I just select a few. And you can actually you can draw in boxes that will select ones for you that are more correlated to the price, for example. You can say, I want the 5 most correlated ones. Then I go through and split the data, 80% for the training and 20% for the testing. And now I've picked 2 different machine learning models, a decision forest and a linear regression. I go through and train them, and when I train them, I say I want to train on the price. And I go through and score them. So I just want to show how one of these models looks. So this is the decision tree, or the decision forest. So recall that I said that in the decision forest you had like multiple trees working together on voting. So each one of these is one decision tree. And here we have 8 of them because you can configure and we configured them for 8. And each one of these now have if statements, like if the land area is over 299, it will go one direction. And here, if the area is over 185, it will go one direction, and so on and so forth. You see here it's like it created a feature called region Edsviken, which was one of the regions. So it will say if that's true or not. And then eventually it will come to the bottom and give a number. So that is how that model looks. Whereas a linear regression model, it will just have the weights for the features. Let's see if it... did I not visualize the right thing, maybe? What should I do? Let's see. OK, so the linear regression model, on the other hand, looks like this. It has like just weights for all the different features that we put in. And then it goes through and scores. And scoring is just predicting a value. So if we look at this, we'll then have all our data, and then we'll have the scored label, or the average scored label. So in this case, we had 4.8 million was the real value. It guessed 5.1 million, which it is a little bit off, but it's quite right. The thing here is that I didn't have a lot of features, so this is not going to be a super good model, but just so you can kind of understand the way it looks. And in evaluate, what it will then do is it will look at these and calculate like the loss function and say how far off were we. And it creates like a bunch of different values or different metrics that you can calculate on. So this is the whole process again, and for 6,000 rows of data, this training takes on average like maybe less than a minute to do. So it's for that little data, it will be super, super fast. Obviously, if you do deep learning, you might have like 100,000 rows, and you might have a very big network, and it could take like months to do this if you don't have like a very nice GPU or a data set in the cloud. Which, by the way, if you're doing deep learning, there are like data science virtual machines that you can run in the cloud. And once you have this model, the model that you like, so the train model, what you'll do then is you'll set it up as a web service, and you'll get an experiment like this. Let's see. If I can pan this like this. OK, so now it's a lot smaller. That didn't work so well. OK, so it's pruned off like the things that it didn't actually need to create a web service. But now you have a proper web service that you can just call with REST. So just like any other web service or any other REST API. You can just call it like that. And you can even use this for retraining, and retrain by basically programmatically sending in new data to the model every so often. So you can do like continuous retraining. And then you use the answer, retrain a model. And here you have it. This is essentially like the full machine learning process from A to B. Hopefully this has been a little eye-opening as far as what machine learning is all about. And I hope I made this hour worth your while. Thank you. Does anyone have any questions, by the way? Everything was crystal. OK, up there.
Download the results from the last thing, but you created a web service, it generated some code, and you download it and run it locally.
OK, so can you download the results of Azure ML Studio and run it locally? No, in that particular case, it will always run up in the cloud, but what you can do typically is, like what you typically will do is you will do it in Python, so you can recreate the same thing very easily in Python, and then you can create a pickle and create like a container that you can run locally if you want to. But just for Azure MS Studio, that's meant for running in Azure. Okay, thank you.